Yeah, hello. In my last class, we discussed the need for using electric energy very efficiently, or the need for conserving electric energy. And in case of induction machine, which is a workhorse of industry, we found the various ways of saving electrical energy. In case of induction machine, to save energy, there has to be a separate power processing unit in between the source and the load. Just by connecting the source directly to the machine, it is just not possible to save electric energy, or it is just not possible to operate the machine where the efficiency is maximum. So, you have to, or there has to be a separate power processing unit which processes the power and which gives the required input to the machine. Okay. Now, let us see in the case of DC machine. See, DC machine has a very excellent control characteristics. It is very easy to control the torque. Armature current and field current are always there at quadrature in 90 degree. Angle between IA and IF is always 90 degrees. Therefore, torque per ampere is maximum. But then we all know the disadvantages. It requires regular maintenance, is not suitable for high speed applications, and various other issues. See, all these limitations are addressed in induction machine. So, induction machine is a very rugged machine. It is capable of running at very high speed. But then whatever the advantage that we had in DC machine is just not there. It is very difficult to control, or torque control of induction machine is difficult. Okay. See in this equivalent circuit, the rotor current, equivalent rotor current and the magnetizing current, the vector sum of these two is the stator current. So, whatever that happens in the rotor circuit will affect the magnetizing current and therefore the stator current. In DC machine, yes, the equivalent, the rotor current and the field current, they are always at 90 degrees. So, we could control them independently. Now, the question is, can I design some sort of a controller in which I can get the characteristics similar to that of a DC machine from an induction machine? Okay. So, I have achieved everything. Induction machine is very rugged. All the disadvantages are of DC machine, they are addressed here or eliminated. So, here is a control scheme along with the power processing unit. I can get the characteristics of separately excited DC machine from an induction machine. Is it possible? We will see whether it is possible or not. By the way, so far I have not told you the definition of power electronics and the goal of power electronics. I will just tell you the various avenues in which you can save electric energy. Maybe towards the end of my lecture, let us see whether you are using power electronics, can we address all these problems? Maybe answer may be very obvious one. So, we discussed induction machine, and let us talk about the synchronous motor, generally high power machine, okay. But then it is not a self starting motor. So, our machine teacher told us that one of the ways to start a synchronous motor is start like an induction machine using a cage winding and excite the field when the speed is approximately equal to this synchronous speed, or when it attains the rated speed, close the or excite the field winding, machine will pull into synchronism. What is the problem here? There is a stability problem. In the sense, if there is a transient loading, if the machine is suddenly loaded, it may fall out of step. Okay. In this machine, the rotor speed is determined by the supply frequency. See, the speed of the synchronous machine is always equal to the synchronous speed, and synchronous speed is governed by the supply frequency. So, in other words, the supply frequency determines the speed of rotation. That in case of a conventional synchronous motor connected to a 3-phase supply. So, can I address the stability problem? See, instead of making rotor speed depends on the stator frequency or stator field, can I generate the stator frequency from rotor speed? See, I will repeat. I am generating the required stator frequency from the rotor speed. So, in case there is a sudden transient loading on the rotor, on the machine, the rotor will decelerate. So, automatically there should be a reduction in the stator frequency. So, if that happens, there is no stability problem at all. Synchronism is always assured. So, is it possible to implement this scheme? Okay. What is another avenue in drives? You see, we are talking about energy conservation. See, take for example, I have a high power machine running a high inertia load. High inertia load, J is very high. Okay. Now you want to stop the motor, you want to decelerate it and bring it to a halt. So, if you put off the supply, which is a natural thing to do, what will happen? Since J is very large, machine will take a longer time to decelerate and come to a halt. See the equation, this is the equation. J d omega by dt plus B into omega is equal to T minus TL, where T is the electromagnetic torque developed, TL is the load torque. So, if I neglect the friction, d omega by dt is given by T minus TL divided by J. So, if I put off the supply, maybe electromagnetic torque will come 0. Okay. So, machine will decelerate depending upon mechanical time constant. All the energy that is stored in the inertia is dissipated as heat, and machine takes a long time to come to a halt. We are talking about energy conservation. Instead of dissipating the energy stored in the inertia, can I recover it and feed it back to the source? Okay. Simultaneously, can I increase the rate of deceleration? Right, like killing two birds in one stone. One is recover the energy which is stored in the inertia, feed it back to the source, and increase the rate of deceleration. See here, see d omega by dt is maximum when I do like this, T plus TL divided by J. I have made it T negative now, T negative. So, if T is positive for motoric action, T negative implies it is a generating action. So, by making T negative, I have increased the rate of deceleration. Now, d omega by dt is T plus TL divided by J. Okay. T is negative, it implies that generating action energy is fed back to the source. So, is it possible to do this or implement this? We will see later. Now, coming to the DC power supply that is used in the laboratory, the regulated DC power supply. In a digital electronics, you require 0 to 5 volts. In analog electronics, maybe depending upon the biasing voltages for a BJT or op amp, it could be plus or minus 5 or plus or minus 12. See, here is a regulated power supply, 30 volts, dual regulated power supply, 30 volts, 2.4 amperes, equivalent to 2.5. So, wattage is approximately 150 watts, okay. Dual power supply 150 watts. See, it is heavy, quite heavy, okay. And see, there are some devices, or there is a heat sink and some transistors are mounted outside. Looks like for heat dissipation, they must be getting hot. That is why they have mounted it outside with a large heat sink and quite heavy. This is what we are using, or you might have used in a laboratory, regulated DC power supply. Okay. Why it is so heavy? See here, another power supply which is used in computers, 200 watts. I can carry it safely in my palm. So light. Why it is so light? 200 watts, and the power supply that I showed you is 150 watts. And there is nothing like a heat sink outside and some transistor or some devices outside. There is only a input AC supply, and these are the outputs. Why this is so light and why this is so heavy? Why is it so heavy? It is so heavy because there is what is known as a very weak element, that is a 50 hertz step down transformer. So, almost all the regulated power supply that we are using in the lab has a 50 hertz regulated transformer, step down transformer. So, can we eliminate this transformer, thereby reducing the size, weight of the power supply? See, when I was a student, maybe in 90s, the speed of the PC was 20 megahertz, PC80. It was supposed to be a state of the art machine, 20 megahertz PC80. Now, the speed is of the order of say 2.4 gigahertz or so, maybe higher, I do not know. The speed of the Pentium machine or speed of the computer is increased. Definitely there are ICs. Okay. So, as the clock speed increases, definitely some of the ICs which are there must be operating at that speed. Okay. So, as the clock speed increases, maybe some of the ICs have to switch or change a state at that rate. There is something known as the switching losses take place. And these losses, they increase with frequency, the switching losses. Now, one way is to reduce the clock frequency, which is just not possible. All of us want a very fast machine. But then I have to reduce this losses. How do I reduce the losses? Another way to reduce the losses is to reduce the biasing voltage itself. Because when the output is high, the output of the TTL may be VCC, and if the output is low, it becomes 0. So, can I reduce the biasing voltage itself? See, I was told that 2 years down the line, the biasing voltage will come down to as low as 0.9 volts. 0.9 volts. So, 2 years down the line, the power supply requirement is 0.9 volts, 100 amperes DC power supply. 0.9 volts, 100 amperes DC power supply. Can we design this power supply using a step down transformer and what not? Is it possible, or do we need to use altogether different technology? We will see. Now, coming to power systems. See, here is a single line diagram, a long transmission line. I have not shown the parameters, okay, transmission line parameters. Here is a sending end voltage, Vs is the sending end voltage. Length of the transmission line is very high. Say I can consider as a long transmission line, which you might have studied in a power system course. And here is the receiving end voltage. Vr is the receiving end voltage. Okay. It is expected that, or it is required that Vr remains constant. Okay. Vr remains constant, approximately 1 per unit. It remains constant. It is desired. But then we find that voltage at the receiving end generally falls with load. And this Vr, magnitude of Vr is much less compared to Vs as the lagging watt demand increases. In other words, if the power factor becomes very poor, lagging power factor, okay, lagging power factor, a large inductive load is being connected here, okay, you will find that the difference between Vs and Vr is high. In other words, if I keep Vs constant, Vr drops. Okay. So, if the lagging watt demand increases, or in other words, as the power factor angle increases, that means lagging power factor angle increases, this magnitude of Vr falls. Now, how do I improve the voltage profile at the receiving end? In other words, how do I maintain Vr at 1 per unit, or how can I maintain that Vr at constant value? I told that one of the reasons for the Vr to fall is the reactive power demand has increased. The transmission line is feeding a large reactive load. So, one of the ways to improve the power factor, which our circuits theory we learnt, is that to connect a capacitor at the receiving end. In other words, we connect a capacitor here. So, this capacitor will supply the required lagging watts to the load. So, therefore, the source will now, the transmission line, or this current is only a unity power factor current. This is a unity power factor current, the reactive demand is being met by the capacitor. Now, I have connected a capacitor to supply the reactive power demand of the load. Voltage at this point is falling. Okay. So, as this voltage falls, the var supplied by the capacitor also falls. See, because it is given by this, Q is VR squared divided by XC. I have connected C at the receiving end, and Q is VR squared divided by XC. So, as VR falls, Q also falls. What is required for the transmission line? As QR falls, as VR falls, Q should increase. See, I will repeat. For the transmission line, as VR falls or the voltage at the receiving end falls, Q should increase. Only then it will try to maintain the voltage at the required value. But here I have connected a capacitor, and we found that as this voltage at the receiving end falls, the Q supplied by the capacitor also falls. So, some sort of a unreliable friend. When you want that friend's help, he is just not there. Same thing is happening here. The capacitor is supposed to supply higher Q as VR falls, but then as VR falls, the capacitor var also falls. A unreliable friend. What is the second thing? You have to vary the capacitance, you have to vary Q. And a smooth variation in C is just not possible. A smooth variation in C is just not possible. It is going to be in steps. So, the question is, can we design a circuit which supplies both plus or minus Q vars, lagging vars as well as leading vars, and it is independent of VR, voltage at the receiving end? I will repeat. Is it possible to design a circuit wherein it should be possible to supply plus or minus Q very smoothly, smooth variation of Q, and it should be independent of the voltage at the receiving end or voltage at Vs. Is it possible? That is a question that I am asking. We will see sometime later the answer to this question. A second case in power transmission. See, consider again a transmission line. I am just representing the transmission line by the reactance XS. Some reactance I have called it as XS. So, voltage at this point I have maintained at V1, and voltage at this point is V2. I am taking V1 as the reference, and angle between V1 and V2 is delta. So, what is the power transmitted through this transmission line? It is V1 into V2 divided by XS into sine delta. This is the expression that we have derived. So, where V1 and V2 are the voltages at two ends of the transmission line, XS is the interconnecting reactance, and delta is the phase angle difference between V1 and V2. Okay. Now, we assume that V1 and V2 are 1 per unit. Now, how did I achieve to get V2 is equal to 1 per unit? We will see later. Okay. Now, we assume V1 and V2 is equal to 1 per unit. So, you get P is equal to sine delta divided by XS. Okay. And again, so see, here is the profile P versus delta, and we have told from this equation we can find that variation is possible. Theoretical variation, theoretical limit is delta is 90 degrees. Delta is 90 degrees. This is a theoretical value. Maybe in actual practice, this delta could be of the order of say 30 to 40 degrees. In actual practice, delta angle between the two ends is of the order of 30 to 40 degrees. 90 degrees is just on the blackboard or on the notebooks, that is all. Now, the question is it possible to increase P, power transmitted to the line, securely? Can I increase the power transmission, power that is transmitted to the line securely? Take for this example. The same thing, see V1 at one end of the transmission line, V2 at other end of the transmission line, delta is the angle between V1 and V2, and at the midpoint, somehow I am maintaining a voltage Vm which is 1 per unit. Okay. See, somewhere at this point, by supplying only the reactive power, I am just connecting a reactive element here. Okay, and making the voltage at this point, at the midpoint of the transmission line, is 1 per unit. Okay. So, there is no active power transfer to the device here, it is just the reactive power transfer here. I am just supplying Q at this point, at the center point. Same condition, voltage at this point is 1 per unit. Now, I can find that angle between V1 and Vm is delta by 2, by symmetry. Okay. So, now what is the power transmitted through this line? The same power will go through to this point. It is V1 into Vm divided by the reactance between it is x by 2 into sine delta by 2 now. Okay. So, this is the expression. Now, I will plot. In the previous case, theoretical limit is 90 degrees, theoretical. Now, you just see, even delta is equal to pi, it is at the peak, theoretical limit again. So, it is possible to transmit a higher power through the existing transmission line by providing some sort of a reactive power support at the midpoint of the transmission line. Okay. Now, what exactly is its unit, or what is to be, or what is the role of power electronics to achieve this? Again, we will see later. Okay. Again, a third application, again in power systems. So, we have a long transmission line, generally power that is produced in the rural areas, a remote end, and bulk is consumed in the urban areas. Okay. So, you require a really long transmission line, and the moment there are long transmission line, there are various problems, stability problem, voltage drop. Okay. Now, can we address this problem? See, instead of transferring the power, that is whatever that is generated directly to the receiving center or to the urban place, can we convert the AC power to DC? Okay. Convert the AC power to DC, transmit this DC power, and again at the receiving station you invert to AC, because power that is utilized, almost all the loads, they require AC. Okay, power that is generated also may be AC. But then if I transmit the AC power So, there is a problem, stability problem, voltage problem. So, what I will do is this AC power we converted to DC. How? Again, I am not answering that question, nor I am telling you how exactly to do this right now. Now, there are only two wires, positive bus DC bus and a negative DC bus. In AC we had three transmission, three lines. Now, there is only the resistance of the conductor that will come into picture, and this DC I will convert it back to AC. Okay. And in this case, let me tell you one thing, there is no stability problem at all. There are no stability problems. Okay. So, this scheme is known as high voltage DC transmission, high voltage DC transmission. So, the question is, can the bulk power be transmitted by converting it to DC? Okay. I will repeat, can we transfer bulk power by converting it to DC? Okay. Answer later. Now, that is about power that is being consumed by motors, and we discussed the various issues in power transmission. Now, third point about the lighting, I said bulk is consumed by motors and second is by lighting. We all know that lumen per watt for an incandescent bulb is much lower compared to that of a fluorescent lamp. Lumen per watt for a bulb is very less compared to lumen per watt for fluorescent lamp or for a tube light, whatever. So, what is the problem in the fluorescent lamp? Oh, bulb we just require a holder and a wire. What do we require here? We require a ballast for what is known as a choke, a starter. Why do you need a ballast or choke? It's because the lamp has a negative characteristics once the arc has been struck. So, I will not go into detail of the working of the fluorescent lamp. I am just telling you that the lamp has a negative characteristics, negative impedance characteristics, negative resistance characteristics once the arc has been struck. It operates at 50 hertz. Okay. It requires a choke or a ballast. Invariably, a magnetics that is used at 50 hertz, they create a objectionable noise. Okay, it's irritating because it is in the audio range. They are lossy. Okay. And overall power factor is again poor. What is another effect? There is something known as a stroboscopic effect, because lamp is being turned off and ignited at every 100 seconds, at every zero crossing. That is something known as the stroboscopic effect. So, this could be objectionable or it could be dangerous in the shop floor, because so assume that there is a blade which is rotating at the same speed, and if both the frequencies match, now what will happen? The rotating blade will appear as if it is stationary. So, it could be dangerous. Actually, it is rotating, but it appears to be stationary. That is known as. So, it could be dangerous. So, what is found is the lumen output of the lamp increases if the frequency of operation has increased. Okay. As the frequency of operation increases, or if the lamp is operated at a higher frequency, lumen output also increases. Now, the frequency of operation is high, so size of the magnetics or storage elements also comes down. Okay. So, as the frequency of operation increases, the size of L that is required, or maybe C at all if at all is required, all come down. And we all know that if the frequency is above 20 kilohertz, it is in the above the audible range. You cannot hear the noise produced. Okay. So, looks like there are advantages by operating the lamp at a frequency higher than say 20 kilohertz or so. Okay. So, one is it is the audible range, above the audible range, you cannot hear that noise. Lumen output is also increased, size of the magnetics has come down. Okay. Also, it is possible to improve the source side power factor. Okay. See here, I will just show you the plot of lumen. This is the lumen output versus the frequency. This frequency in kilohertz, please, not hertz. We have only 50 hertz supply. I have plotted for kilohertz. See, maybe 100 at a very low frequency of 50 hertz. 50 hertz, it could be around 100. It attains a peak around say 20 kilohertz or so. Okay. So, again we have a 50 hertz supply, and here I need to operate at 20 kilohertz. I need a frequency converter. Okay. That is about lighting. So far we discussed about the issues or avenues wherein to save power or to transmit more power or to improve the power transmission capability, we need to have a separate equipment. Okay. Now, let us see energy from the alternate sources, because in order to extend the whatever the life period that I told you, those the so called 200 years, I have to use one way to use it very efficiently, another way is to look for other alternative sources. Yes, see here is a overall picture. Okay. The energy from non-conventional sources or the renewables. Okay. See, if you go back to the historic energy sources, our ancestors, forefathers, they used a very simple technology. Using wind power, wood, okay, and hydro. A very simple technology they used to produce power. Slowly we transformed to today's energy sources. We used oil, coal and nuclear. Okay. Just now I told you that so these power stations are invariably located at remote end. So, that has to be transferred to the load centers, generally the urban places. The future trend is going to be what is known as the distributed power generation. In the sense, If there is a demand, you set up a small power plant there itself. Instead of generating the power maybe around say 300 to 400 kilometers away, transmitting it. So if you want, if there is a small load center, you set up a small plant, okay, using renewables and try to feed the local area. What is known as the distributed power generation. Okay, that's going to be the future. Okay. So again, the future is going to be using renewable sources like solar, wind power, biomass, hydro. So it looks like wheel has completed its one round. See, we were here, our forefathers did this. They also used wind power, hydro. The future is also, it's been projected, and it will be true. It's going to be solar, wind power, biomass and hydro. Future, and this is historic. Looks like one complete circle, or the wheel has completed its circle. Okay. Now, but then what are the issues here? Fine, in the sense solar and wind, they consider to be very clean. Okay. But we all know that solar is bit expensive. Solar is expensive. But the silver lining is cost is falling, it decreases. Cost per unit is decreasing. Okay. And another problem with solar is output is DC, is a DC power output. And most of the loads except for incandescent bulb maybe all require AC. How about wind? Supposed to be very the cheapest, environmentally clean. See, it is projected that, see here, this is what is reported in the literature, wind energy now provides more than 31,000 megawatt of power around the world. This is reported in the literature. And in India, the installed capacity is 1900 megawatts. Installed capacity is 1900 megawatts in India, is nothing new to us then. And our target is to achieve 6000 megawatts by 2012. Okay. And it is also estimated that wind could supply 12% of the world's electricity demand by 2020. It can supply world's 12% demand by 2020, just the projection, certainly projected. But then what is the problem here? Solar is DC, something definitely you need to have one more power processing equipment. Wind, we all know that one is, it is highly unreliable. Okay. See, that is the problem with the non-conventional sources. Solar, unreliable. On the cloudy day there could be no power at all. Wind, again it is seasonal. Fine, even if it is seasonal, what are the problems there? As the wind speed changes, okay, there is a turbine. The speed at which the turbine is rotating, the rotor of a machine also changes. Okay. See the block diagram here. So this is a variable speed. Okay. So therefore, the magnitude of the voltage as well as the frequency is a function of the wind speed. Okay. It's like, conductor is rotating in a magnetic field. Voltage induced in the conductor is proportional to the speed of rotation or the relative speed, and second is the frequency also depends on the speed. So, at this point we have a variable frequency AC source. Okay. Grid requires a constant voltage and constant frequency source. Okay. You cannot have a grid wherein the frequency and voltage varies over a wide range, but here is a wind, the speed is varying over a wide range. So, definitely there has to be some sort of a power processing unit. Okay. What is this power processing unit? We will see sometime later. See, there are directly grid connected induction generators are there, but then nowadays the so called fixed speed, the moment I connect an induction generator directly to the grid, the speed, the frequency, state of frequency is determined by the grid, so rotor speed also is fixed now. It should be higher than the synchronous speed. But then nowadays the variable speed wind turbines with permanent magnet machines are gaining popularity. They have become increasingly popular. Variable speed wind turbines, see here, variable speed wind turbines with permanent magnet machines, they are gaining popularity, increasingly become popular. So, what is the problem here? Again, I told you just now, output frequency and the voltage is a function of speed, magnitude is a function of speed. Okay. This requires constant frequency, constant voltage. So, you require a power processing unit. Okay, what is that power processing unit? Last one, urban pollution. Okay, can be decreased by the widespread use of electric vehicles. Instead of having a vehicles which are operated in gasoline, you have electric vehicles or say hybrid electric vehicles. So, if you use electric vehicles or hybrid electric vehicles, there is going to be a significant reduction in urban pollution. Yeah, we all know that gasoline based vehicles are efficient at a particular speed. So, what you do is operate the IC engine at that particular speed, and other speeds motor driving the wheels. Okay. So, thereby you can reduce the pollution as well as save the fuel. Okay. So, that is about the various avenues where which you can either save energy or try to make a difference in improving the quality of life. There are many more still left. Now, before discussing those issues, I will give you the definition and goal of power electronics. See, here is that. So, power electronics is the technology associated with efficient conversion and control of electric power by power semiconductor devices. See, I will repeat, is the power electronics is the technology associated with efficient conversion and control of electric power by power semiconductor devices. And what is the goal of power electronics? It is to control the flow of energy from electric source to electric load. See, here is a block diagram. There is a source, here is the load, interfacing is done by a power electronic equipment. Okay. So, depending upon the nature of the source and the nature of the load, this equipment or the configuration also changes. Why is this power electronics so popular? Why it is being compared with computers? I said two technologies will dominate, one is computers, another one is power electronics. Why it is being said that power electronics is an enabling technology for distributed power generation? I told you the future is going to be distributed power generation, and power electronics is the enabling technology for distributed power generation. Why it is being said that power electronics provides the lifeblood for communication equipments, electronic systems and computers? Okay. Or in other words, why this is so popular? See, the success of any technology, it depends on the following. It should be highly efficient. This. Second is, it should be reliable. Okay. Third, the size, weight and cost should be low. See, maybe it's amount to going against the law of nature, because it may not be possible to achieve all these factors like high efficiency, high reliability, okay, size, weight and cost low. Rather very difficult to achieve all these factors. Let us see which are the factors that can be achieved. Take for example, what happens if the efficiency is high? So, if the efficiency is high, it implies that there is low power loss. So, if there is low power loss, cooling requirement or the heat sink requirement comes down. Okay. Now, the power loss is low, temperature rise is also low. So, I can package the various elements very densely. In other words, packaging density can be increased. If the packaging density increases, size comes down. Okay. So, if I try to achieve high efficiency, okay, I can achieve other parameters also. Looks like the efficiency of this power supply unit must be very low. That is the reason it is so heavy, and it is being, there is a large heat sink and components are being mounted outside. It is heavy, whereas the efficiency of this must be high. That is why it has become so small, compact and so light. Okay. So, how this power electronics achieves this, we will see it in the next class. Thank you.